Okay, so I'm continuing on a relatively similar topic, and that's using machine learning for spatial and spatiotemporal prediction. So I'm going to talk about the paper that, so most of the things I will talk about is explaining a scientific paper, and this paper took a long time actually to produce, more than 2 years. Some things just take a lot of time, but what is nice and what is symbolical that I got the first idea about to do these things. The first idea I got was the geostat in Lancaster. So that was the first time I went and I pitched that idea, and that was the idea to use machine learning as a spatial interpolation framework. And so we had this paper, and it's been accepted recently in PeerJ. I'm very happy about PeerJ, by the way. It's a very nice process, and they also opt for whether you prefer that the review results are also published. And so I said, yes, I have no problem with that. So you can see actually how the paper evolved, and you can see all the discussions, so you can trace back. Just to zoom into that paper, I recently looked at the statistics, and it has almost 2,200 downloads. So I think there is some interest in this, and I think it's a relatively broad topic. And we are now looking actually at a couple of spin-offs. So it's a bit of a vision paper also, and we are looking now at a couple of spin-offs. And the most interesting spin-off of this paper is the use of machine learning for spatial temporal interpolation. So we're trying to integrate both time and space distances into modeling. How we published the paper? We made a paper through collaborative writing, and we published also all the code and all the demos on GitHub. Through R Markdown, so you have this computing notebook, and you can follow all the steps, so there shouldn't be any mistake about the results we get, so you can validate all our results. And the tutorial, which you can find on this URL, it's more extensive than the paper. Paper is already about 45 pages, but tutorial is even more extensive, so it has even more examples and comparisons. And this is something I'm going to try to show in this session. So when I started doing my PhD, that's back in 2000, I was then, my mainstream framework for spatial analysis and spatial prediction was using geostatistics. And that was, again, I was one of the users of Ezer's GStat package, and also later on I started using GR package. And kind of these kriging techniques, they've been a synonym for geostatistics ever since 1960s. So it's been now already 60 years. So there's like 60 years of kriging, more or less. And now I started looking at some properties of machine learning for spatial prediction, spatial interpolation. I discovered that it could be a replacer for kriging. And so it could be that we're looking at the end of kriging techniques. So that's a possibility, but that's what we wanted to explore in the paper. The paper was actually about that. So something about kriging. So in kriging, you have these assumptions, and there's quite a mathematical derivation of properties of different assumptions and different models. But typically what you do is you have to know the distribution of your target variable. So you have to look whether it's normal or you need to do some transformation. Then you fit the variogram, and that standardly is done using some Remel or weighted least squares. Then you can plug in some covariates, and these covariates you have to see whether there's a multicollinearity. So maybe you have to do principal component analysis. There can be some mixed effects. And then you do predictions. And as an output of prediction, you get a map showing the predictions, and you have a map showing you the kriging variance. So this is the measure of the model uncertainty. And then you can do validation. And I think in GStat, if you do krige cross-validation, this actually takes just the existing variogram and just applies it with subsetting the data. So these are kind of standard steps. I tend to use now a bit more GOR than GStat because GOR has a few more options to fine-tune the variogram fitting, and I like the idea that the GOR works with the transformation and back transformation, so I think that's something we shouldn't be playing with. So that's why I tend to use GOR. So these are two steps in GOR. It's the model, the fitting of a variogram through the ligfit function. And as you see here, we have to define, for example, lambda 0. It means that we want a transformation. And then we also have to give some initial variogram parameters. And we pick up the type of model we want to use. So we have to specify a couple of things. And then we also, when we do kriging, well, kriging is more automated. Once we fit a variable, then we just do kriging. And then the kriging will do, in GR you get this. If you do a transformation, then it will fit a variable with transformation. And then it will do a back transformation, so you don't have to play with that. And then you get the final map. So that's kind of state-of-the-art geostatistics, I think, in R. In my career, I worked a lot with extending the kriging to using also covariates. So for me, that's kind of a hybrid system. I like the name for this technique, the name I like is regression kriging, because you do regression, you do kriging. But some people also call this group of techniques universal kriging or kriging with external drift. And so I've been working on that, applying that technique to different type of data for about 10 years. And I think if you Google that term, regression kriging, there's a good chance you will find my name. And now people, in science you get identified with the term, right? If you do some scientific field and if you're good, then if you Google that term, then they find you. So we are actually just some terms in the science. And so if you Google that term, there's a good chance you'll find me. And now people come and tell me, hey, you're the regression kriging person. And I stopped using geostatistics more or less and kriging techniques about 3-4 years ago. So yeah, that's also happened in science that, yeah, as you move forward, there's a bit of a delay. So people come and say, hey, you're the guy using regression kriging. I said, no, actually, I don't. So did they get the wrong person? No, you just came in the wrong time. So that was what happened to me. And also, I think if you look, I did a bit of a Google trend search, and you see the red is the kriging and blue is the machine learning. Random forest technique only, and you see there's a bit of less and less interest in kriging and a bit more and more interest in random forest. I think this is just the Google Trends data, so it doesn't mean that it really applies. But let's say, only in Brazil I see that the interest in kriging is still more significant. In Italy also? Okay, Italy and Brazil. So you saw now in the previous talk that you can do machine learning with the spatial data and spatiotemporal data, but we often we ignore some things about this data. For example, we ignore the location of points, and we don't use the location of points in the model building. And then Hannah showed you, okay, you can take the location of points, but then you can make it even worse. You make these artifacts. So on one hand, ignoring spatial autocorrelation and spatial autocorrelation structures in building models for machine learning, it's kind of suboptimal, but it also looks to be suboptimal if you just plug in the XY coordinates. And so this is the things I knew already five years ago. So I was thinking, how could we overcome that problem? So what's the way to go around it? And so I came to this framework where you basically, the most generic idea of that framework is that you have 3 types of covariates. So you have the geographical covariates, and they explain you relationship between points and space. Then you have the reflectance covariates, so this will be satellite images with multispectral bands or radar images. And then you have a process-based covariates. So these are the covariates you prepared specifically for your target variable, where you represent processes which can approximate formation of that variable or changes in values. And so this was all, let's say, relatively new, but what is this geographical covariates? So I started looking how can I plug in geography without using the XY as coordinates. And first thing that came up to my mind is, okay, let's just calculate buffer distances. Okay, so if you have 10 points, you calculate 10 maps. And so that was easy. I tried with a lower number of points. I made my own functions to calculate that at once. So you just say, these are my points, and this is the grid definition, calculate me all the buffer distances. I even run that now in parallel. So it's straightforward. But once I started working with more points, I noticed, okay, if I have 150 points, I need 150 buffer distances. And then I was worrying, maybe I'm over-parameterizing. Maybe I will have, you know, in statistics, in regression modeling, as a rule of thumb, they recommend that you have at least 10 observations per covariate. And recently I started fitting machine learning models where I have more covariates than points. Okay? And I wasn't sure whether that's something you can do. But that was the first thing I started thinking, and then we started extending that. We started thinking, okay, buffer distance is also like, you know, this is just Euclidean distance, so they're relatively trivial. But we started looking, there's also G-distance package, and a very nice package made by Van Etten, I think, and Heymans also. And so this one allows you also to, if you have a digital elevation model, you can calculate this effort distance. So if you have an area where you have to cross over hills or something, that will be most distant. And if you have an area which is just like Netherlands, you know, with a nice bicycle, you go very far. And so you can calculate these more complex distances. And then also, there's a couple of algorithms where you can derive watershed distances. So you calculate the upslope distance, downslope distance. So you can calculate very complex distances. And so I started playing with all these things. And just to come back to the Euclidean distances, I made this little function called buffer dist. So you take a point map, and you say, this is my target variable, and you say, calculate the distance to all points. And once I get this distance to points, I just do overlay. So I will make an overlay to get the values of all distances, right? And from there on, it's just machine learning. And then I take a ranger. I usually run things in ranger because it's computationally efficient. And also because they collaborate with the main package developer. And then you just say, so zinc, target variable, is a function of distances. And then you do prediction, and that's it. And so take a look at this. This is the GOR state of the art. It's quite sophisticated. You have to define this transformation. You have to define the initial variogram. Then you do a REML to fit the variogram. Then you do a prediction, then you do back transformation. So there's quite some sophistication, state-of-the-art geostatistics. And this one, you just go path distances, random forest prediction. So you don't need any transformation, you don't need any assumption, you don't need to fit a variogram at all. Okay, and this is the difference. So I was surprised with that. I said, wow, this looks pretty similar. There is some, here you have this, so the legends are the same scale. And I think the color legend police might arrest me, but I don't know, I just like this rainbow. I mean, you really have to arrest me, I just like it, so. Which I'm not, I don't want to say that like you should all use it. I think it's a personal preference which legend you want to use. for me, much more important thing is you have access to the data, by the way. So when you see this is here, this blue is a bit bigger than here, and it's a bit more complex. And this thing looks a bit like smoothed out. And I was thinking, why does this happen? But because random forest is an ensemble, and so if you do like 150 trees, then it will bit smooth out because it averages, especially if you have a lower number of training points. Then I took another data set, just, okay, let's show data sets. On the end, we tried about 20 data sets. I don't have time to show you all of them, but I really wanted to show whether it's consistent. And that's another data set, also smaller data set. Again, GOR, again, transformation, log normal, Hengl to fit a variogram, etc. And there's a prediction. And here you see even more smoothing. So these high values get smoothed out, and also low values a bit higher. So the high values are under-predicted, low values are over-predicted. So that was when the data sets were smaller. When we took a bit bigger data set, this is a data set from the SIC, I think it's SIC, is it? SIC 97, yes. It's a famous data set. There were, I don't know, something like 50 geostatisticians trying to produce the maps, and they were very nice. The SIC exercises, they stopped, unfortunately, some 15 years ago. But SIC, by the way, stands for Spatial Interpolation Comparison. So the organizers will prepare one data set, and they will give it to groups of people, and they will give them time. And then different groups will try different approaches that they feel familiar with, that they think they are most promising. And then they will come meet at one place, and then they will look who made the best comparison. And then they will publish a report. And then they will say, these are the winners, right? There was, I think, 1 year, I think it's not with this data set, with a 2004 data set. One person just visually went, looked at the points, and drew by hand predictions. And made it to the 3rd place, I think. Yes, yes. So yes, everything goes, I think, in this prediction comparison. But in our school, in the spatial prediction competition, we don't accept anything which is not reproducible. So you cannot do by hand. And you won't be able to do by hand because there's 6 million. We have a training set with 6 million rows. So you cannot do it by hand, I'm pretty sure. But anyway, so we took a bit more complex data set, and then we again ran this machine learning. In this one, we use the geographical distances and the covariates. So it's a whole thing integrated. And we also calculated the uncertainty. So we predicted the uncertainty. So this is the random forest, and this is the GOR. And they are both displayed on the same scale. And so what happens here? So this is the rainfall in Switzerland for 1 day, and it has a relatively strong anisotropy. So when you model that, you estimate the anisotropy coefficients, and then you plug them in, and then as a consequence of that, you have this pattern, which is like there's an angle in the predictions, right? And then I wanted to see what's going to happen with machine learning. And machine learning finds this anisotropy, but because now the data set is bigger, this is some like 300 points, I think. And so this data set is bigger, and what machine learning now shows that it doesn't have a global model. So it can have a spatially global. It can have an anisotropy here, but here it can be, let's say, here it's isotropic. Okay? So it will locally adjust. And this one is equally anisotropic in the whole area because it's just a single model. And this one, I see that, okay, there's some anisotropy, but then it can be also isotropic. Also, we looked at the kriging. This is the kriging variance, and this is the random forest upper and lower difference between the upper and lower interval predicted using the quantile regression random forest. And we see you get a much more contrast. Okay, you get much more contrast, and we notice that what happens is usually it's somewhere in the valleys or in the areas where there can be like 1 or 2 points that have serious problems in the internal validation of the model. And so we see, okay, this gives a much more contrast. Like here we have a very little contrast. We just see as you go further away from points, you get a bit higher errors. Because these are, like everything you do in geostatistics, basically it's that you work with transformations, but usually these are just linear models, whether they're general linear models or simple linear models, but they're linear models. And here you have like a really non-linear things. And so we noticed, okay, that could be interesting. And then the next thing we did, we went and looked, okay, let's do space-time. And I was surprised actually how the extension was then trivial. Once you set it up, and once you test it and you understand what's going on, then the extension to space-time is we just added, so this is the cumulative time, and this is the day of the year. So this one you use to model seasonality, and this one to model changes through time. So you just add the time. So you have a distances in space from points, and you have distances in time, and you put them all together, and you fit a space-time model. And as I said, this is something very promising because we realized that we can produce prediction space-time, and so here it goes. So this is coming from the kriging ST from GStat package, and this is a model fitted by Ben Greller and predictions made. So I just gave him the data. So here's the data set. It's a daily rainfall. It's a very tricky data set. It's a zero inflated variable. And there's not many actually papers published on doing it. What is the exact mathematically correct or statistically correct procedure for zero inflated variable? So he tried improvising a bit, but eventually he fitted a space-time variogram, and he made the predictions. And then I said, this is the prediction I get with this method we used. So what happened here, what do you see? So there's a 1 point which had a high value, and you see it comes back both in kriging and in the random forest. The predictions come high. But you can see that this is area, I just actually came from this place, I was last week there. So this is Boulder, Colorado, somewhere here, and Denver is, I think, somewhere here. And so, and this is the start of the Rocky Mountains, right? And you can see that sometimes you have a rain will happen on the plateau, but not in the mountains, because there's a really sudden jump of elevation. You go like from 1,600 meter to 3,000 meter. And so the machine learning picks up this boundary between the plateau and the mountains. It picks it up. Well, here it's also visible, but it's less. It's more smooth. When you look at so these are the prediction intervals, prediction error. And when you look at the random forest, again, you have much more contrast. Very interesting results. This single station, which had a high rainfall for that day, you see now it has a high error. And that error actually impacts also other days. So as you go further, the next day and day after, you can see that this high error impacts the further in the time. Okay, just this station. So it impacts not only in space, but it also impacts the prediction error in the time. And we also see that the prediction errors are, in random forest are the highest where you have these transition zones. So you go from a plateau to a high area. So yeah, very interesting results. And in comparison to the kriging variance, you see that you get more contrast. Now, question is this really more information? Is this really that we add so much more information? I mean, if you compare information content of the maps below and these maps, you talk about some tens or more time information. So the question is it really more information? So we did a lot of comparison. We tried many times, and it is, as you get to the bigger and bigger data sets, the added value of doing this uncertainty is higher. It gets higher and higher. Also depends on how accurate are the models, right? So if you have models which have a relatively higher accuracy, then also the uncertainty estimates are higher. So that's what we've been testing, and that's what I want to show you in a bit of a demo, so that you see that I'm not fantasizing. So I will show you that with the real data. And as I said, everything I will show, more or less, it's either described in the article, or you can go to the, let's see, you can go to the repository, and then you can follow step-by-step guide to the machine learning for spatial prediction. I have to decrease the font size. So I'm going to just run now a few things just so you get an idea with the real data, and I will be really interested to see whether you could maybe use this technique with your data, and if you will use it, and if you experience something, I'm here for you this week, so you can come and ask me. And while I'm talking about this, I am running now space-time machine learning on a big server, and I am trying to process this data set for the spatial prediction competition. And I'm now running the whole data set, as you can see. It takes 5 hours and 29 minutes more, because I'm running 6 million rows with something like, what is it, 350 columns. Okay? And so this, I'm running in the background space-time interpolation for this data set that I'm going to describe you in the next session. And you see, this is when you fully optimize it. It takes a lot of RAM also, 159 gigabytes of RAM, and it's running on 64 threads. This is Ferrari I have at home. We are lucky to have that machine, so we can do serious projects. And so we've been testing this for different meteorological applications also. And we run it now on millions and millions of records. So when you do in a space-time domain, you can easily, as you stack, if you have measurements every half an hour or every 15 minutes, you easily come to millions of observations, right? Especially meteorological stations. So while I've been doing something on a little data set, I just wanted to show you that I don't waste time in my professional career. There's always something in behind, some computing going on. Okay, so that was this comparison of, the script is called random forest versus kriging. Okay? So I'll just run a few examples just to show you how things look like. So it doesn't seem too abstract. So I load all these packages. And I load the Ranger package. And there's also a nice package called Tune Ranger. So this is a bit more sophisticated tuning of Ranger parameters. So then I said in geostatistics, I like to use the GR package. So to use the GR package, I will first convert the data to this geodata class. So when I convert it from the SP to geodata class, and don't ask me why they don't use the SP class, I don't know, but they decided to use class which they call geodata, and which has XY coordinates and has a data separate. So you see the spatial reference and the data is separated. It's similar kind of in the SP, with the SP classes. So once I have this geodata, I can specify the initial variogram, and I will specify it simply by calculating so I take the variance of the target variable, and I take some distance, which can be, for example, 1/3 of the range of the area. And so I specify the initial variogram parameters, and then I can do link fit. And you see it says, be careful if you do it with the big data. It can be demanding. This is a fitting quite sophisticated actually, because it's a REML-based approach and it optimizes. So it tries to fine-tune the parameters. And so let's say that's like a state-of-the-art geostatistics. If you want to use geostatistics in R, I think the functions you get in GR, I think, offer you really some for variable modeling, things offer you really state-of-the-art that you will find in literature. And then you can do also the REML in GStat, right, Edzer? But the transformation, back transformation, you have to do yourself.
From what?
For the target variable.
Yeah.
Yeah, so.
It's too long.
Okay. So we fit so I set up an initial Variogram. I fit the Variogram using Remo, and then I can do kriging. And you see this kriging also has a back transformation step. And it's nicely, I think it's very nice in Geo that it informs you, so it's not a black box, it informs you what are the steps, like general steps, what type of interpolation you're using. And then when I get the predictions, I can copy them in the spatial object. And I can also get this kriging variance. So I think if I plot this, so I will get something like this. Let's see. Except I cannot plot it now because I switched to the, but what I could do plot KML. Let's see now. So then I get something like this. So these are only the predictions, right? Yes, I'm not getting any PNG because my PNG drivers died because of my projector resolution. Okay. So that was the ordinary kriging, but as I said, I cannot visualize it, so I can just show you. I can show you here in the slides. That was this thing. That was the first example, the mass data set. So that's what came out of the ordinary kriging. Or maybe yes. Okay, I cannot visualize it in R, but I can do a write GDAL. I'm going to do that. And let's see. I have to pick up a file name. So I can write to results, I guess, mass. So let's see, where is this? Results, and then news, and then I will call it ordinary kriging. Okay. What else do I have to define? No, that's it, I think, right? Okay. So let's try to open that in QGIS. I hope the projection system is preserved. Well, let's try this. So that's this one. Okay, so that works. Now I'm going to pick up a legend. My favorite legend. Don't use this legend, right? Where is the legend? Yes. Okay, and let's put something in the background so we can see, let's see, satellite. Okay, so these are the predictions from ordinary kriging with the log transformation. So you see there's a few places where the values are high. Let me also write the points. So that's the there's a points. Well, I can write the whole thing. I need to put the layer name. And I have to say it's a S3. A bit of. Okay, so I can add the points now here also. And we'll make a nice display so we can see the differences. So here the points, on the points I can put the labels. And this is the zinc. So now we can compare the observed and predicted. Okay? And then now we do machine learning. So machine learning, much more simple. Basically, you just need the distances. Distances can take a bit of time, you see, because I calculate now distances, and let's take a look. Well, actually, the plot will not work. I'll try it one more time. Yeah, no. So the distance is very simple. It's just the buffer distances from point to everywhere in the area. And then I define the model. The model is a bit, it looks, so here's the model. So we can talk about it. But it's a long formula. Basically, zinc is a function of buffer distances. Right? Imagine if I have 1,000 points, then it will be zinc a function of 1,000 distances. And the computing will then get heavy. But there are ways to go around it. I can talk about it also later. And then I do overlay. And then what I do, this is in the script, I will do the tune ranger. It's a nice package developed by a colleague in, I think, from Munich. And this allows you to, because there are 4 parameters of random forest, so if you really want to get the perfect parameters, then you can do this tune ranger. So it takes a bit of a time. And then I can copy these parameters, so now when I do the ranger, I will use exactly the parameters I got. And this one tells, okay, R square 52%. And then I can do predictions. And then again, I copy these values. And now I can also do I can write these things again to the folder, except now I'm taking the RFD. So random forest using distances only. Okay. And now we can compare. So I will just put exactly the same legend. So here's the difference between the two. Right? So there are some differences. Maybe I zoom out a bit. So yes, there are some differences. Definitely. This one will show a bit of jumps in the values, and this kriging is kind of always smooth. I mean, kriging is, you cannot, like, I mean, you have to have some crazy kriging parameters. And the random forest can be smooth, like here you can see it's a bit smooth. But then here you have a high sudden changes. And what happens here that you have a one single point, which is like isolated high point. And then random forest tries to come close to that point, but because it's a single isolated point, then it smooths it out. If there were 2 points which were high, probably wouldn't smooth it out. So you see here, there's more points which are high values. Then they don't get smoothed out, but these points which are isolated, they get smoothed out. Whether this can be remediated, I'm not sure. But I think I have now really, because I use the tune random forest, I think I really got the best random forest parameters for this data set. So this is as good as you get with the random forest, I think. If you just have the points, so that you have no covariates. So this was the random forest approach. And then, so there are many other examples. I think I have reached my time limit. Yeah, so there are many more examples of with the random forest applied for spatial prediction. And so what I do further here basically is I just keep on adding stuff. I start adding covariates, then I start adding process-based covariates, then I start adding time, and we just develop it. And we also realized that with random forest, because it's a kind of decision tree system, we discovered that you could just take one model. So if you have a stack of variables, let's say the mass dataset has some 7 or 8 geochemical elements. And so you could make one random forest model that takes 7 elements and you fit it at once. So you can do multivariate model fitting. And also we discovered that you can also extend it to space-time problems, and you can combine it with different types of distances. You can have even like at the same time you use the buffer distances and watershed distances. So you can really keep on extending it. It's a kind of a platform to do machine learning for spatial prediction problems. So that was what I wanted to show you on machine learning. And if you're really interested in this, then take a look at the paper, and we will have tomorrow, day after tomorrow, we will put a list of topics, and you can then vote for these topics. And then some of the topics we'll do in the evening session, and then some of the topics we might do on Friday. But if one of the topics you're interested in is this machine learning for spatial temporal prediction, then I can do that on Friday. And I could then show you example with the spatial temporal data and how you make a spatial temporal maps. You make a time series of predictions using machine learning. Okay. Any questions before yes? We need a microphone. How many of you knew about this? How many of you knew about random forest or spatial data? Okay. Okay, I see about 10, 12 hands. So it's not too much of a shock. Yes.
Hello?
Yes.
Why did you use the random forest algorithm and not another machine learning algorithm? So what was the reason that you choose the random forest algorithm?
Yes, there's no special reason except we just wanted to start comparing machine learning techniques for spatial prediction, and we pick up a random forest. One of the reasons, pragmatically, because Marvin made a package which is very efficient, it's scalable, right? So you can run it with a lot of data. And also I like about random forest that it's an ensemble technique, and I think ensemble is really promising. But it could work with any. I think the only requirement for this approach is to use some machine learning which is like a tree-based. There's a tree-based system behind. Because the advantage of this tree-based system that you can localize spatial autocorrelation and spatial patterns. You can localize them, right? And that comes up. I know I spoke now with the geostatisticians, and some of them, they were a bit shocked. They will say, wow, this is now, it's really end of the kriging. So that was a bit of shock. And then, but some started saying, well, what I really like about this is that you don't have to have these assumptions, like stationarity assumptions. And that's where they got really, they said, oh yeah, because it was always, we always had a discussion about it, and it's always, you cannot test it, you have to do all the assumptions, and you never know whether it's correct or not, so it was a bit slippery. thing in geostatistics. And now we don't have to have these assumptions because basically your data will tell you whether you have a like a local pattern or you have a pattern that is spread over a big area. And that was visible, I hope, from this Switzerland example, where you have a both like an isotropy and you can have a locally some variation which doesn't have to match the variation other side of the study area. But it will be interesting to test other. So like if you're interested, take the same data and try to do some other cubist, I don't know, or do some gradient boosting machine or something. But try to test it, see what happens.
Thank you.
Yes, Robin, and then Edzer.
Where do you submit the results to the competition, and can we use the same place to submit entries to the visualization?
Okay, competition is coming. I'm going to talk about it. So it's coming. I mark your question. And Edzer, you want to also say something about this topic?
Well, so you swap one method with the other, but I can't imagine that sort of random forest doesn't make assumptions about your data. So
absolutely, yes.
I mean,
yes.
it's not like without assumptions that you
absolutely,
assumptions and then suddenly do not make assumptions about your data, but still can make prediction. I can't understand that.
No, yes. There's when I just started doing this random forest for spatial prediction, then I realized, okay, looks promising. But then once I did like 20 data sets and I tried different things, and then I started discovering all the drawbacks. So there are many problems, right? I'm not trying to tell you this. Number one problem we discovered is the extrapolation. If you do extrapolation with a random forest, and this is, I think, the best way to visualize that is this plot that I stole from a colleague which wrote a blog about extrapolation with the random forest. So you see, when you do a linear model and where the points end, you can apply that linear model. And as long as the assumption that there's a linear relationship, that helps you to extrapolate that model. It's not going to make damage. But if you extrapolate the random forest, it will just remember the last thing in the variable space. And because it's a decision tree, it will say, okay, this is the last thing that happened, so I apply it for anything beyond. There's no structure, really. There's nothing. And so the extrapolation will result in this type of things. And we noticed that, and what we discovered then, and that's why I said, look, just because we have machine learning, it doesn't mean that there's no need for geostatistics. No. It's just it's a different approach. And now what I realize, that now when you do sampling, and if you want to apply machine learning, you have to be about 20 times more strict. You have to be really strict about sampling. And you have to use sampling designs, and you have to make sure that you cover all the space and you minimize extrapolation effects. Because you can really hurt yourself with machine learning. You can create, often we create so many artifacts that in average, over the whole area, because of this extrapolation problem, the results will be worse than some simple geostatistical approach, even inverse distance interpolation. Okay, so it's a very sensitive to location of points in space, and very sensitive to extrapolation, very sensitive to blunders. I had machine learning models for interpolation where I had a 1 point, which was a typo. Instead of 6, it was 600, because instead of dot, they used the comma. And it will have such a high impact, right? Which you wouldn't get that high impact if you use just kriging, or if you use some, like this robust regression or something. Then you can adjust for that. But machine learning, it's a data religion. So if your data is like that, machine learning tries to adjust everything to the data. Yes, last question, then we have to switch to the spatial prediction competition game.
Could you explain again the buffers you used and what that and how that works? I wasn't able to follow along how the buffers were used. What does it mean using the buffer as a predictor variable?
Yes, okay, so I'll try one more time. Don't try to think, I mean, it's embarrassingly simple. You have So let's see, how's that? So here is a function that takes, so this function buffer dist. So it takes set of points, and you have to give it a grid definition, and then it calculates from each point distance to all other pixels in the grid. You just get this buffer distance to the single point. And then you calculate that for each location. And you get, if you have 156 points, you get 156 rasters. Okay, and then you say the model relationship between the target variable zinc in this case and the predictors is this. So zinc is a function of distance to first point, distance to second point, And this, if you will go and fit a linear model, this is nonsensical. So any statistics or geostatistics you will do with that, it's over-parameterization. But for machine learning, it's no problem that you have 150 covariates to predict from 156 points. I can take 50 points and I can take 500 covariates. And for machine learning, that's not a problem. I mean, it's heavily over-parameterized, but because it has a built-in adjustment, which is you do ensemble and there's the bagging happens, and so it adjusts for that.